Hello, good morning everyone. This is Casey from Semicon Techno Labs. So let us continue with the floor planning topic. So this will be part 2 closure of the floor planning topic. So we are Semicon Techno Labs, which are leading provider of VLSI and embedded corporate trainings and internship programs. So over 8 years of experience, headquartered in Bangalore and having branches in Hyderabad as well. Alright, so about the presenter. So I am Casey, having 19 plus years of experience in VLSI and currently working as Senior Director at Radiant Semiconductors, taking care of end-to-end product development. Alright, so we'll recap last week's floor plan presentation, and then we'll go to the part B of today's floor plan presentation and then conclude the presentation. So last week we discussed about ASIC flow. So where we have system specification, architectural design, RTL design and verification, synthesize the design, and then physical design, where we have placement and routing, and then sign off. Again, in placement and routing, we have floor planning. This is the topic which we are discussing right now. And after physical design, we have mask generation, fabrication, packaging and testing, chip. Okay, so this is the complete cycle for ASIC design flow, all the way from specification to the finished chip. Okay, and then this is a cycle where from chip design specification, we are going to architectural design, followed by behavioral RTL coding, and then followed by functional modeling, which is nothing but structural RTL coding, and then logical implementation, where we are mapping the RTL into netlist, and then synthesis and testing, where we are optimizing the PPA, and then after that we are doing the testing and then adding the DFT logic, right? Then PNR, and then followed by design layout. Okay, similarly, to go a little deeper, right, I mean chip specification followed by design entry or functional simulations, followed by RTL synthesis, partitioning of chip, right, and then design for test insertion, floor planning. This is the topic which we are discussing, and then placement stage, where we place the standard cells, and then clock tree synthesis, where we do the optimization of clock DRVs, that is max stand, max cap, max fan out, right, using the clock buffers and clock inverter pair. And then routing stage, where we do detailed routing based on the track assignment, which again depends upon the global route. And then final verification, it can be physical verification or it can be any of the other sign off checks, for example doing STA using the sign off extraction, followed by writing the ECOs for timing closure, or it can be low power checks with respect to UPF and CPF. Again, it can be static checks or it can be dynamic checks. Okay, and it can be formal verification as well between post PNR netlist and synthesis netlist, or post PNR netlist and RTL as well. Okay, and finally, once the checks are completed, even including the EMR checks by Red Hat tool, then finally we will have GDS2. Okay, or nowadays we are having OSs as well apart from GDS2. Okay, now let's look at the physical design introduction, which we discussed last week. I will just again touch base the same, right? I mean, if it is a very big design, especially top down approach, right, I mean we will go with partitioning the bigger design. There are several advantages of partitioning the bigger design, as we know, right? I mean, we can parallelly implement the partitions or the blocks, right? I mean, without waiting for a full chip to be completed. Parallelly, we can implement the blocks, and finally we can assemble them at the full chip level. Okay, that is one advantage which will help us to minimize the turnaround time and to meet the TTM, that is time to market. Okay, now partitioning, once partitioning is done, again we need to be little careful here during partitioning, because the port locations what we are providing to the blocks and the PG mesh what we are providing to the blocks, right, I mean that should be carefully defined here in the partitioning, so that it will be easy for us in the end to assemble the blocks. Okay, so it is always good that we don't depend on the trial route, we go with the detailed route. And similarly, with respect to placement of cells, right, usually we go with coarse placement, but it is recommended to go with the legalized placement. Okay, now this is on the partitioning part, though it may take some runtime, but it is always suggestible to go with correct by construction approach. Okay, so once partitioning is done, right, then at the block level the first step would be floor planning, because we already have the die size and die shape defined by the partitioning owner, right? And then even the port locations are predefined as per the partitioning. Of course, we may have some liberty to modify the port locations as per the requirement of the block or as per the requirement of the neighboring block, maybe requirement of the floor planning as well, based on the placement of the macros. Okay, but then the primary goal of floor plan, as we have discussed last week, is like, the first point is to minimize the white space that is present in the die area. So to optimally come up with the die area and even die shape as well, considering the metal layers what we have, horizontal and vertical routing metal layers and vertical routing metal layers, right? And similarly the type of macros what we have, and the shape that has been assigned to us by the full chip team based on the partitioning that has been done. Okay, so always remember, if at all we need to go for increase in die area or reduction in die area, or let's say change in the shape of die area, we need to have it closed with the full chip team, right, as it will impact the neighboring blocks. Okay, now floor planning, again coming back to the goal of floor planning, one is like reducing the die area or giving the optimal die area with minimal white space. That is one topic. Second goal, I would say, is to come up with a routable design. That's the main important thing, right? I mean, routable design. When I say routable design, we need to make sure that global congestion is in control. The macro to macro RAM channel that is been given, that is in reasonable stage, I would say, without wasting the white space, right? Sometimes we give 6 microns, 8 microns, 10 microns, but then we need to bear in mind that any additional area what we are giving, and if we are underutilizing the RAM channels, then it is directly impacting the silicon area. So we need to be cautious in choosing how much of RAM channel we need to give between macros and how much of RAM channel we need to give at the edges of the macros. Okay, those which are placed at the edges and they are talking to the IO ports. Okay, now power planning, as we know, I mean, like to define the PDN network to supply the current to all the cells that is present in the design, and of course placement is like placing the remaining standard cells that are present in a legalized way, and then optimizing the PPA. Clock tree synthesis, as we discussed, like the goal of clock tree synthesis is to optimize the clock cells for DRVs, that is max try, max cap, max fan out, and the target of clock tree synthesis is to check for skew1 latency. Okay, this is needed for performance and as well as for reduction in the area and power consumption. Okay, so skew, of course, directly related to the timing closure, and then latency directly related to the area and power consumption. Okay, now signal integrity, right? Again, we have global route, track assignment, detail route. So global route, it will be there all the way from floor plan, because that is where we define the global congestion. Similarly, in power placement as well, we have global route, that is where we define the local congestion. And then we have track assignment and detail route. So track assignment just follows the global routing based on the G cells that are present in the global routing. So track assignment based on the routing direction of the metal layers, either horizontal or vertical. Accordingly, it will lay the tracks for the respective metal layers, right, based on the global route. And detail route will just follow the track assignment. However, it can lead to DRCs, that is physical DRCs. It can be spacing violations, it can be shorts, which will be again taken care during the search and repair operation. Okay, now after signal routing, we need to focus on the parasitic extraction, physical verification, formal verification. These are some of the sign off checks, right? And then make sure that parasitic extraction, especially after PNR, we are using the sign off tools such as star-RC extraction. Okay, and then these extracted files will be used in static timing analysis. Nowadays we are using the star-RC extraction even in physical design as well, so that we don't have to have any net delay variations between the PNR and as well as the STA tools. In order to minimize that gap, we are trying to get the star-RC extraction even into physical design, right? Now we do the STA. It can be different type of STAs, DMSA based STA, regular STA, right? Or different modes of operation can be enabled. Even the SDC file which we are using in PNR, it may have specific scenarios, but then in STA, the SDC which is being used, that is the final SDC, right? Where like all the scenarios has to be enabled, and we need to make sure that the design is perfectly meeting the performance requirement, right? It can be related to not just performance but even CDC checks, special checks, right? Special timing checks, all those things has to be met. Okay. Now, once STA is done, including SI and non-SI based STA, right? Now, the next step is to make sure that IR drop is completely clean, right? I mean, even with routed database, we don't see any dynamic IR drop issues, especially switching related, and similarly, like short circuit power consumption as well. Okay, and then finally tape out. Of course, before going to tape out, we have a lot of things to take care, right? I mean, we need to make sure that our checklist is proper, right, and correct way construction has happened, reviews are happening, jiras are closed, right, we are aligned with the customer on the exceptions what we are applying for the design, right? So many things go in place, and finally we move the database to tape out. Okay, all right. Now let's go to floor planning. Okay, I will just recap on this one because we covered it last week in detail, right? Now, as you can see, floor planning is a very important step in the physical design, I would say. If you break the physical design into two parts, right, part 1 and part 2. Part 1 especially unit design, floor plan, power plan, placement, right? So floor plan is the key here, right? If we don't do the floor planning properly, we will end up with lot of issues at the later stages of the physical design. Especially timing closure will be difficult for the from memory and to memory violations. Similarly, clock gating violations will be present, right? And then lot of wastage in white space, right? I mean, which is expected because floor planning has not been done properly. Routing issues will occur because congestion is not in control and lot of detours are happening. Okay, so a lot of things go in place. That's where, like, in the entire first half of the physical design cycle, it is always recommendable to spend quality time for doing the floor plan. Okay, now as you can see here, right, I mean, we have followed some of the floor planning guidelines, like all the macros are placed at the edges, they are not at the center, so the detouring of the nets doesn't happen. Okay, and as per the module, right, I mean, based on the module, the coloring has been done. You can see here green, blue, red, right? I mean, based on the modules, again, we need to make sure that the macros are placed properly. Okay, so we need to have a fair amount of understanding on how the module distribution is in the given design, right? And then which modules are having how many macros, how many port connections, how much of logic is present in each macro. And if it is a low power design, then we need to identify what are the voltage areas we need to create, what is the default voltage area, and how many macros are sitting in each voltage area, right? And how they are connected to the macros present in another voltage area, how the clock tree has to be built between the voltage areas, right? Again, it's the next level of challenge, I would say, if you have voltage areas, right? Again, in voltage areas, if we have same voltage, right, I mean, the power mesh will be simple. But if we have different supply voltages for different voltage domains, right, and then these different supply voltages are coming from different sources of the block, are coming from different sources of the chip, right? Then in that case, again, we have to define the full chip power mesh and the block level power mesh accordingly. So I would say that complexity of the chip keeps on increasing, right? And then somewhere we need to have a robust flow so that we don't we are not prone to errors. Okay, so that's where the importance of floor plan will come into picture, because your power mesh is purely depending upon how good you do the floor plan. Okay, the ram channels which you are keeping here in between the rams, right, especially between the pins and pins connecting between the rams, right? At the facing of the pins, we need to keep the ram channels, more ram channels, right? And how you are defining your power mesh so that power can be distributed even in these ram channels without causing any EM and IR drop issues. Okay, so these kind of things we need to take care, right? And it is recommendable even to check with the designers if they have any data flow diagram documents which they can share it to the physical design team, so that instead of just depending on the data flow fly lines and on our understanding of the netlist, right, it is good that we discuss or have some info from the designers as what best floor plan can be done, right, which can meet the PPA as per the spec requirement. Okay, now moving on, we'll just brush up on some of the floor plan inputs and steps, right? So initialization of floor plan of appropriate dimensions, that is nothing but die size and die shape. It again depends upon whether you are going with a top down approach or bottom up approach. right? If it is top down, the dimensions and the shape will be given by the area and the shape will be given by the full chip team. If it is bottom up, then the area and the shape has to come up from the PNR engineer, physical design engineer, right? And then once the shape is defined, area is defined, then macro placement has to be done, followed by the placement of IO pins. Okay, so sometimes we'll have confusion whether to place pins or whether to place macros, but rule of thumb is always to go with the macro placement, because there are certain macros which has to be placed at certain location. Their location cannot be changed by the user, right? It again depends upon the placement criteria of the macro given by the full chip team, or placement criteria of the macro given by the neighboring block owner. That's why it is recommended to first place the macros and then follow the IO pins placement. Okay, then macro placement considers the communication between them through fly lines. Okay, so we have a feature in both Fusion Compiler and as well as in Innovus. Even we have feature in ICC2, or previously also in ICC and Encounter we had the features of checking the data flow fly lines, right? We can check up to level 2, level 3, level 4, right? To what extent we want to check in order to understand the connectivity of the design. Okay, now as we can see in the diagram, so these are the trunks, right? I mean, first these are the pads. From pads, the power and ground supply goes to the trunks, and from trunks it goes to the rings, and from rings to the straps, and finally to the rails. Okay, and again we have horizontal layers and vertical layers. Okay, so it is always recommended as soon as we receive the input files for starting the physical design, right? It is recommended to have a thorough understanding of how many horizontal layers are there and how many vertical layers are there in the technical file. Okay, applying appropriate placement blockages near the macros, near the IO pins, densely packed cell areas. So we have to be cautious here, right? I mean, placement blockages, whenever we are applying, we need to remember that placement blockage will directly block the silicon area. It will block the core area, right? None of the cells will be allowed to place there. Again, it depends upon which type of placement blockage you want to use, right? It can be hard, soft, and partial placement blockages. Okay, so please be cautious in using the placement blockage, as it will eat away your existing valuable silicon area. Okay, and the placement of tap cells, boundary cells, and end cap cells. Once you place your macros, before we move to the PDR network, right, it is recommended to place your physical cells, right? Now tap cells which will supply the bias connections, right? Boundary cells which will terminate your bias connections, and then similarly end cap cells. Pretty much I would say boundary cells and end cap cells are the synonyms, right? Some PDKs call it as boundary cells, some PDKs call it as end cap cells. Okay, now going to the floor plan guidelines. Okay, I will just brush up on the floor plan guidelines which we discussed in part 1 of this presentation. Okay, so floor plan guidelines, right? I mean, the placement of macros is based on the fly lines, which is nothing but data flow fly lines. We call it as DFF, data flow fly lines. It shows the connectivity between macro to macro and macro to standard cells. Okay, so we can minimize the interconnect length between IO pins and other cells. Okay, so now the main advantage or main usage of data flow fly lines is fly line analysis was done to locate the macro families, right? We need to understand what all macros are falling in the same hierarchy. Okay, and connections with the standard cells and ports. We also need to understand how each macro is connected to the logic that is present in the design. Similarly, how each macro is connected to the ports that is present in the design. Flyline analysis helped to understand the importance of flipping and positioning the pin locations of the macros to reduce the wire length connectivity. So this is nothing but the orientation of the macros. Okay, we need to make sure that we are maintaining the poly unidirection as well. And then once we maintain the poly unidirection, then whichever flavors of orientation is allowed based on the poly unidirection, right? We need to make sure that the ports or the pins of the macros are facing towards the core, right? They are facing towards the neighboring macro which is talking to it. They are facing towards the ports which is talking to it. Sometimes the orientation will not be followed properly in the floor plan, which will again lead to congestion and connectivity issues as well. Okay, the nets has to be detoured, right? And then of course the wire length will increase, which will again lead to the net delay, increase in the path delay, which will again lead to the timing issues. Okay, so orientation is one main thing, right? I mean, so step one, I would say, right, which is defined here, is first to come up with the macro locations based on the data flow fly lines. Once you come up with the macro placement based on the data flow fly lines, the step two is to come up with the orientation of the macros. The location will remain same, but the orientation has to be changed. Okay, and then this orientation, the first preference is to make sure that it is following the poly unidirection rule. Okay, now continuation to floor plan guidelines. Once we placed the macros and the orientation is fixed, right, during the initial floor plan placement we shall perform fly line analysis followed by fan in fan out techniques. During the next floor plan iterations, this will help us to converge design with less iteration. So of course one iteration will not be possible to finalize the floor plan. Multiple iterations has to be done, and it is always recommended to have a review of the floor plan with the designers. Okay, so please make sure before proceeding to PDR network placement, CTS routing, it is always recommended that you get a review with the designers, especially the RTL designers and the architects, if the blocks are complex in terms of PPA. Okay, so that you have the blessing of them saying that the floor plan is matching as per their expectation, as per their blueprint, right, what they are expecting, or maybe as per the previous projects, right? And then once the floor plan is blessed by as many folks as possible in the design team followed by the PNR team, right? You can even have reviews done by the another block owners as well, who are PNR engineers working in another blocks as well, because few things which we may have missed out may be caught by the another PNR engineers working in different blocks or different projects. So cross review, we call it as cross review. So it is always good to have as many reviews as possible, either with the designers or cross reviews, right, to make sure that we don't end up with any problems in the floor plan before we take it to further steps of the PNR, because it will be a challenge to again come back and redo the floor plan and repeat all the steps, right, considering the schedule and efforts involved. Okay, place the macros around the boundary of the rows as we saw it in the very beginning, right, leaving some space between the macros to the core head, so that during optimization this space will be used for buffer or inverter insertion, and keeping large areas at the center of the core area for placement of standard cells during the placement stage. Okay, macros that are communicating with pins or ports of the core, place near to core boundary. All right, place the macros of the same hierarchy together. This is again the same thing. We need to always make sure that we keep an eye on the hierarchy browser, and then using the hierarchy browser we make sure that the coloring of the macros are coming properly and they are all located at the same location. Okay, keep a sufficient channel between the macros. This is again the RAM channel. Keep an eye on this. Underutilized RAM channels will lead to wastage of the white space. Okay, avoid notches while placing macros. If anywhere notches are present, then use hard blockages in that area. Okay, some people use hard blockages, some people use soft blockages, right? I would recommend to use soft blockage based on the average scenarios what we have seen, but in few cases, right, I mean, we have to go with hard blockages. Okay, right, and then avoid crisscross connections of macro placement. Create a keep out margin around the four sides of the macro, so no standard cells will get placed near macro pins. This technique avoids global congestion. Okay, keep placement blockages at the corner of the macros. For the pin side of the macros, keep a larger separation, and for the non-pin side, right, we can abut or adjoin the macros with their halo, so that area will be saved and the halo of two macros can be abutted, so that no standard cells are placed in between macros. So always make sure that when you receive the macros database, right, please cross verify whether the halos are already present inside the macros, or do we need to create the halos outside. Okay, so this will help us to save on the area, because we are not additionally creating extra halos in the core area if halos are already present in the macros. Okay, also, right, I mean, wherever there are no pins for the macro, we don't have to give again the same kind of RAM channel which we are giving at the locations where pins are present. Right, now wherever we don't have pins of the macros, there we can directly abut the macros, provided halos are present inside the macros. If halos are not present, at least we need to have 1 macron or 2 macrons of halos, and we can abut the macros. Okay, so these are some general guidelines. There is no hard and fast rule that it covers everything, but then in general, to certain extent, we can mitigate global congestion, we can mitigate the wastage of the white space by following these golden guidelines. Okay, now floor plan guidelines, right? Again, continuation. Between two macros, at least one pair of power stripes, right, should be present for a non-abutted floor plan. Okay, we need to make sure that between macro to macro, at least two stripes are coming. One is VDD, one is VSS, right? Or I would say one pair of stripes is coming, that is VDD and VSS. Okay, if the stripe itself is not coming in the RAM channel, then it becomes difficult to supply power and ground to the cells present in the RAM channel. Okay, multiple iterations happen to achieve an optimal floor plan. The chip designer takes care of the design parameters such as power, area, and performance during floor plan stage. Okay, and also as you can see here, the blocks with highest performance and highest power consumption, right, they are placed close to the boundary where power pads and IO pads are placed. Okay, this will help in reducing the IR drop and similarly EM. Okay, so whichever blocks or whichever IPs or whichever macros that are having highest power and highest performance, it is always good that you place them close to the power and ground IO pads. Okay, so that the supply rails will be as minimal as possible. Okay, if you place these macros somewhere else, right, and the power and ground pads are away from them, right, then whatever the stripes we have connecting from the pads to the macro, those stripes will have again the resistance factor, which will again reduce the IR drop. Okay, so that's the reason, right? I mean, we need to make sure that the blocks are placed close to the power pads. Okay, now some sanity checks before we go to the floor plan, right? I mean, what are those sanity checks? One is like design or netlist checks. Okay, only if the design and netlist checks using the check design command, which is the common command, I would say, in both Synopsys and Cadence tools. Only if the design or netlist checks are proper, then we go for timing checks. Again, in timing checks, check timing is the common command what we have across any kind of tools. Okay, front end, back end, Synopsys and Cadence tools. Okay, now library checks, as I mentioned last time, so library checks are already part of the design and netlist checks. Okay, so now we don't have to do the library checks separately. Okay, the library checks are already taken care in the design and netlist checks. Okay, and we need to make sure that library checks are clean in the design and netlist checks. The reason being, if libraries are not proper, n number of problems will come. Okay, sometimes the timing calculation will be abnormal, right? I mean, it will not reflect the proper DRV violations, nor it will reflect the proper slack violations. Okay, so libraries should be proper, right? Because everything is depending on the library, especially in the timing world. Okay, now let's move to the die size estimation. Just we'll have a quick recap. Okay, so before we go to the die area calculation, we need to make sure that we have die size estimation done and all the metrics what we are using here, right? For example, G, T, E, D, I, M, U, right? All the different metrics what we have discussed here, right, previously. So all these metrics, once we have the values, okay, these values will be put into the formula in order to get the die area calculation. Okay, so generally the rule of thumb is like, if it is a low power design, we give another 5% of the utilization area. If it is a lower technology node, another 5%. So let's say, for example, lower technology node we start with 40-45%, then lower power design we start with 30-35%. Okay, that's how we start. Okay, we don't want to go in a very aggressive way, so that in the end, if there is any functional ECOs that needs to be done, in the end if there are any timing ECOs that needs to be done, or let's say in future, right, I mean for next phase of the project, if we have to add some more functionality using the spare cells, right, or let's say once the BTO is done and then we want to do some changes in the design using gate array cells before we go to MTO, even that time as well, it is always recommended to have some space, extra space available. But then make sure that you are not leaving too much of extra space in the design, because again it will be problematic, not just in wasting the die area, but then it will be problematic in closing the timing as well, because the cells will be spread across. Okay, so come up with a reasonable optimized area, right, die area, which is suitable for your program and which is suitable for your block. Okay, there is no hard and fast thumb rule as such, right? No one formula works for everything, right? I mean, we have to try out different type of approaches based on how your die shape is, what is your aspect ratio, right, how you want to do the floor plan, right, what changes you can expect. Let's say you are expecting changes at the macro level, some more macros are expected to come in phase 2 or phase 3 of the project, then you need to make sure that the die area is able to accommodate them without again going for increase in die area. Similarly, let's say RTL is evolving, right, and you are expecting another 10% increase in RTL, right, in phase 2 or phase 3 of the project. At that time as well, we need to make sure that that extra area is still available in our die area calculation. Okay, we don't have to struggle when more logic is getting added through the RTL. Okay, all these things go into play based on how your program is designed. Okay, now let's go to the limitations of setting up die size. Okay, once you come up with die calculations and die area estimation, right, I mean, again, we cannot directly implement them. The reason being there are certain limitations which we need to take into account. For example, one is pad limited, another one is core limited. As we can see in the diagram, even though the core area is very small here, right, the pad limited design is mainly dominated by the IO pads. Okay, so what happens is, like, since the pad limited design is mainly dominated by IO pads, no matter how small your core area is, you still need to have a bigger die area. Okay, because it is dominated by pads. Similarly, vice versa. No matter how less you have pad area, but the die area is determined by the core area, right? So this core area, right, I mean, it will dictate your die area. Okay, so core limited and pad limited, right, these are some limitations. Okay, sometimes you will have limitation on the package as well, right? If the package for the design is chosen before the die size is set up, the package limits the maximum die size because each package has a maximum space for the die. Okay, sometimes package also will be a limitation if you have to reuse the package. Okay, you don't want to invest again the money for redoing the package activity, you want to just reuse the package. In that case, the package area also will be a constraint where you cannot increase your SOC area beyond the package area. Okay, so these kind of limitations also will be there. So full chip designers who are taking care of the area, die area, right, please make a note that, I mean, these limitations are considered beforehand, right, while coming up with the SOC area. Okay, now what are the different types of floor plan? Okay, so very quickly let me go through, like, there are three different types of floor plans. Abutted, as you can see, there is no gap between block to block. Non-abutted, we have a channel between block to block. And mixed, right, few areas we have left the channel and in few areas we have not left the channel. Okay, you can choose whichever floor plan is convenient for us at the top level. Okay, so then moving on, floor plan control parameters. Okay, what are the different control parameters we have in floor plan, right? So main thing is aspect ratio. As you can see, height by width, that is the aspect ratio. Okay, so we need to make sure that aspect ratio is considered in the very beginning before you come up with the die shape. Okay, now because this is depending upon your number of horizontal resources and again the vertical resources. Okay, as soon as you have the block collaterals in hand, try to understand how many horizontal resources are there, how many vertical resources are there, and using these, how to come up with the appropriate aspect ratio which will dictate your die shape. Okay, so these are the control parameters, I would say, for the floor plan. Okay, now core utilization, this is one of the common terminology which we keep hearing in the floor plan world. Okay, so core utilization is nothing but the amount of percentage which we are leaving, right, in order to accommodate how much of CTS cells we are about to add, how much of DRV cells we are about to add, the routing which we are about to do, and the hold optimization which we are about to do. Right? We need to have enough room to accommodate all of this. Okay, so that's where we need to come up with core utilization. Let's say core utilization is 60%, which means the existing synthesis netlist can be accommodated in the given 60% of the core area, and the remaining 40% will be used for routing, will be used for adding cells in the CTS, will be used for adding cells to fix the DRV violations, will be used for adding the hold cells, right, needed for hold fixes. Okay, that is nothing but delay cells. Okay, this is core utilization. Now, standard cells row utilization. What is standard cells row utilization? If you see both the peaks, low standard cell utilization, high standard cell utilization. Okay, so standard cells are placed, but there is lot of white space wastage here. in the left image. On the right image, standard cells are placed, but it has been used to the maximum extent. Okay, practically we cannot have everywhere cells present because it becomes difficult for the router to route, but at least we need to make sure that we are using the standard cell utilization to the maximum extent possible. Okay, we need to always see whether the standard cell utilization is high, as can be seen in the right image. Okay, if you have something like left image where like low standard cell utilization is there, then it is an alarm for us to recheck whether the die area calculation which we have done and the die shape which we have provided based on the aspect ratio, whether it is proper or not. Okay, now IOs in the floor plan. Okay, the IOs, right, I mean there are again two types, chip IO and block IO. Right, chip IO is the one which will communicate to the package. It will get our signals from the package, similarly power and ground from the package, clock signals from the package, analog signals from the package. Right, now block IO is nothing but IO ports which are connecting to the logic that is present in the chip. Similarly, block to block communication. Okay, so for block we call it as IO ports, and for chip we call it as IO pads. Okay, now let's go to the part B, right? Part B of the floor plan. So we have different placement blockages in floor plan which we can use, right? One is soft placement blockage, hard placement blockage, partial placement blockage, halo or padding or key port margins. Okay, now hard placement blockage, as we already know, right, I mean like it will not allow anything to be placed in that particular area. Soft placement blockage, only a buffer can be placed, right, nothing else, right? Whereas partial placement blockage, based on the percentage which we are giving, accordingly only that percentage of cells can be placed. Okay, now halo, padding, keyboard, this is nothing but for a macro, as you can see here in the light orange color. Okay, these are the halos around the macro. Okay, wherever macro moves, these halos also will move. Okay, now wherever the halo moves, wherever the macro moves, right, it will not allow the standard cells to be abutted to the macros. That is the advantage. Okay, the primary difference between a halo and a placement blockage is the placement blockage will not move along with the macro, whereas the halo will move along with the macro. That's the primary difference. Okay, the synonyms for halo is keyport margin, right, and then padding. Okay, and padding also can be applied for standard cells. Let's say we have complex standard cells where congestion is an issue, local congestion is an issue because of high pin porosity cells. Okay, now if you add the cell padding to these high pin porosity cells, automatically, right, the cells, the neighboring cells will not be sitting closer to those complex cells. Thereby the router will get enough space to route the high pin porosity cells, which are nothing but complex cells. Okay, now we need to be cautious in using which kind of placement blockage we need to use for our floor plan. All right, next, standard cells in the floor plan. What are standard cells? We have two types of cells basically in a given design. One is standard cells, another is macros. So standard cells are smaller in size, macros are bigger in size. Okay, now standard cells, again, it can be sequential cells or it can be combinational cells. So sequential cells are controlled by the clock, whereas combinational cells are not controlled by the clock. Okay, that's the primary difference. And sequential cells can store the data, combinational cells cannot store the data. That's where in the timing path, if you see between two sequential cells, that is register and register, we have combinational cells which is performing the combinational logic operation. It can be AND gate, OR gate, NAND gate, NOR gate, etc. Okay, now when it comes to bigger cells, again it can be memories, which are nothing but again the sequential cells, which is nothing but bigger flip-flops, right? Or it can be macros, which is nothing but analog IPs, or it can be third-party IPs, right? Or it can be few of the yield monitoring cells given by the foundry, right? So many things come into picture. Okay, these are all bigger cells which we call it as macros because they occupy multiple site rows. Okay, all right. Now let's see how we qualify a floor plan. Now, following all these guidelines, all these control parameters, all these limitations, all these calculations, all the different type of placement blockages, all the different type of routing blockages, right? Once the floor plan is done, how do we qualify the floor plan to take it forward? Okay, of course, as I mentioned, one option is to get it reviewed with the designers, get it reviewed with the neighboring block owners, right? I mean cross PNR teams, right, to make sure that we are not missing anything. But then we should also have a kind of checklist on how do we qualify floor plan. Okay, so How do we qualify it? I mean, few points has been noted down here, right? For reference, all macros should be placed and fixed. Don't leave any macro in the placed status. Okay. Once the macros are placed, please change their property to fixed. Okay, they should not reflect as placed, because there is a high probability that during placement, the placer engine may move these macros by seeing it as placed. So always make sure that once the floor plan is done, all the macro locations are in the fixed status. Okay. All IO pins must be placed and fixed. Block should have a uniform standard cell area. Avoid notches. Legality checks must pass. There should not be any overlaps between memories and blockages. Okay, this will reflect as null shots. Okay. Try to place memories across boundary areas unless it is not a design requirement to place them in the center of the design. There must be at least one VDD and VSS power strap between memories to avoid IR drop. Okay, not just IR drop, even EM as well, to improve signal strength at the macro pin by inserting buffers. Okay, try to maintain free space in front of ports to have easy access for standard cell talking. Pre-placement timing can be checked like IO timing, macro to macro timing, and macro to standard cell timing with margin after power plan. Okay, this is very much important. If you don't do the floor plan properly, we cannot meet from MAC and 2 MAC timing. Okay, IR drop must be considered during synthesizing power networks for establishing connections of VDD and VSS rails and standard cells and macros. Okay, some companies, some methodologies, they even club PDN network into floor plan. If that is the case, then please make sure that you have enough power rails running, enough ground rails running, so that there is no static IR drop. There is no static EM drop. Okay. There shall not be any floating pins and floating wires in the layout once the power plan is done. Of course, once we do the PDN network, right, we have to make sure that there are no floating pins. The PDN network doesn't contain any shorts. It doesn't contain any opens. IR drop and EM is completely clean. And even for some projects, we need to always make sure that physical verification LVS is coming clean. Okay. Now, coming to the conclusion of the part 2, right, that is floor plan topic. Okay, the quality of the chip is defined by the quality of the floor plan. A well optimized floor plan results in more efficient utilization of the core area, thereby aiding the placement of standard cells without causing an issue related to congestion, timing, IR drop, and signal integrity, etc. The bad floor plan affects the area, power, and reliability of chip functioning and requires more back annotation efforts. Okay, we want to avoid this. That's where this entire discussion is happening. We want to avoid the back annotation effort. Okay, and ECO activity for design closure, which increases overall IC cost also. Bad floor plan leads to worst timing, which is nothing but from memory and to memory is difficult to close. Congestion is difficult to close. Clock gating violations are difficult to close. Okay, and not just that, even you will end up with noise, IR, and EM issues as well. Okay. So with this, we'll conclude today's part 2 of the floor plan presentation from Semicon Techno Labs, right? And see you all next week with a wonderful topic. Okay, happy learning. Thank you so much for attending the live session. And please do leave your comments, questions, and we'll be happy to go through them and then reply back as soon as possible. Okay, thank you all. Have a nice day.